Okay, so question number 10. What is the ground state electron configuration for each atom and ion pair? Okay, so first we have nickel, and then we have nickel 2+, B, we have manganese. Do it in a different color because it might get a bit crowded. B, we have manganese and manganese 4+. C, we have Y, which the name escapes me right now because it's not commonly used element. And D, Ta. Okay, so let's start off when we need to write the electron configurations for a certain atom or an ion. We first need to separate our periodic table into the different orbital shells. So for example, these first two columns is the S block, and this green part is the P block, and the middle transition metals is the D block, and the last two rows, which are the lactanides and actinides, is the F block. So then starting from hydrogen, we move left to right across the periodic table, writing the row number and then the block letter, and then we kind of just go in order of increasing energy levels. And then once we get to the D block, you'll notice that when we write the row number, it's going to be the row number -1. And similarly with the F block, it's going to be the row number -2. Okay, so let's start off with nickel, which is found right here. So its atomic number is 28. And then starting from the hydrogen, we write the row number, which is 1, and then the block letter, which is S. And then in the superscript, it tells us how many electrons are in that orbital. So we have 1s2, and then going on to the next row, we write 2s2, and then moving across to the p orbital, we're still in row 2, so 2p6, which is the electron configuration of neon. And then going down to the next row is 3s2, and then 3p6, and then now we're going to the fourth row, but in most cases we like to write in order of which energy level, like of increasing energy level. So instead of writing 4s2, I'm going to start off by writing 3d and then counting up to where our nickel is. So we have 1, 2, 3, 4, 5, 6, 7, 8, which brings us to the nickel. And then I'm just going to write 4s2. Okay, so these are kind of cut out. Let me just rewrite it. Okay, so this is the ground state electron configuration for nickel. So now let's see what happens if we were to remove 2 electrons. So now nickel has a positive 2 charge. So since 2 electrons got removed, they were removed from the 4s orbital. So now our new electron configuration looks the same, except the last two 4s2 electrons are now gone. Okay, so this is the electron configurations for nickel and nickel 2+. Now let's move on to the manganese. So again, we'll find it on the periodic table, which is somewhere. Okay, so we end up in 4s. Yeah, so it's right here. Atomic number 25. And we basically just need to do the same thing. So 1s2, 2s2, 2p6, 3s2, 3p6. And then again, I'm just going to write my 3d before my 4s. And if we were to count it up to manganese, it's 1, 2, 3, 4, 5, 3d5, then 4s2. So then when we remove 4 electrons, then our new electron configuration becomes 1s2, 2s2, 2p6, 3s2, 3p6, and then 2 electrons from the 4s orbital are now gone, and then 2 more electrons from the 3d orbital are gone, so it becomes 3d3. Okay, so it's bugging me. I want to find out what the name of this element is. Yttrium. Cool. So it's found atomic number 39. And since it's pretty like down there, we can write the shorthand electron configuration instead. So when we write the shorthand electron configuration, we find the noble gas that comes before yttrium, which is krypton, and we just write it in square brackets. And then we just continue writing the remaining electron configuration. So for yttrium, I'm going to write the 5s2 first, and then 4s1. And then when we remove that last electron, it's just 5s2. So notice that this time I took an electron from the 4s orbital, and this is because, the 4d orbital. And this is because since there's only the one electron there, then it's most likely to just lose that electron than to take it from the 5s orbital. So this is just a reason why, like, sometimes with the transition metals, it can get kind of confusing. But typically, a partially filled d orbital is more stable than like when you just have a filled s orbital. So this is why for our other examples, we took from the d orbital instead of the we took from the s orbital instead of the d orbital. And now let's move on to our last element, Ta. Let's find it on this periodic table first. So this is called tantalum. So tantalum is found here. And again, let's write out the shorthand configuration for tantium. We would write xenon in square brackets. And then we would continue on to name the remaining we would go on to name the remaining electron configuration. So in this case, let's write out our 4F first. So also, the F block is inserted where this red line is. So we also have to take that into account when writing out our electron configuration. And since it's at a lower energy level than our 5D and our 6S, then we would write it first. So it goes 4F14, and this tantalum is found here, so we need to write 5D3, and then finally 6S2. And if we were to remove the 2 electrons, then our new electron configuration is xenon 4F14 5D3. Okay, so now let's see what the junior tutor said. The electronic configuration is composed of the principal quantum number together with the subshells SP, D, and F. And the superscript of the subshells are the number of total electrons in that shell. For this problem, the ground state electron configuration is the electron configuration of the natural state of the element. Meanwhile, the electron configuration of the ions affects the superscripts of the outermost subshell of the atom. So when you have a positive charge, this means electrons were lost, and when it's negative, this means they were gained. So now let's look at nickel. So ground state nickel has, the same electron configuration. And since the outermost shell here is the 4s, having 2 electrons removed will make the nickel ion change its electron configuration to end in just 3d8. And for manganese, they got the same thing. It will end in 3d3. And for this yttrium, I believe it's called. When it loses the 1 electron, it loses it from the 4d1 orbital. So now it's just krypton 5s2. And then lastly, for this tantalum, it has the same electron configuration as xenon, and then 4F14, 5d3, 6s2, and then losing 2 electrons becomes 4F14, 5d3. Yep, so this solution is correct.